All right, I feel like your examples don't do a very good job in the book of actually doing a Taylor series. So let's do an actual Taylor series one here. So I'm going to do 11.3.28, and we want to find the first four non-zero terms. And the series. Okay, and Taylor series. So, we already did that, whatever. So we're going to find the Taylor series, and then we're going to find these first four non-zero terms of this. F of x is equal to cosine of x, and a is pi. So we're centered around that a, which is pi in this instance, so it's not the Maclaurin. It's not the Maclaurin, so I can't use those common ones. All right, because pi makes a difference. If it were pi over 2, that would make a difference also, right? As I'm looking back through here. So then that changes things up a little bit as we're going through there. Anytime you're centered at something other than 0, you cannot use those Maclaurin series, because then that affects that shifting centered at something else affects it. But with cosine here, the first four non-zero terms are not going to be as easy. 0. So we're going to have to do several. 2, 3, I don't know, take it down to 6. Is that what we did before? 4, 5, 6. Let's try that. Okay, so I start off with the cosine of x. So cosine of pi is -1. Ooh, that's the other reason why I like this one. That's right. Okay. And then the derivative of cosine is sine, negative, and that's 0. So I have negative cosine x, which would be a positive 1 then, because it's putting in pi and the cosine is -1. Then I have sine of x, which is 0. Then I have cosine of x, which is -1. Then I have the negative sine of x and negative cosine of x. And that is where we come up with these. So I know that's a 0, that's a 0, that's a 0. So I've got 1, 2, 3, 4 terms. All right, so let's see what we've got on this. I know my first term here is just straight up -1. Now, my second term is a 0, so I'm not going to write that 0 in there. What I'm going to do is I'm going to then look at the next term that I have right here. I know 1 is my numerator. And then I've got 2 factorial there, and x minus pi squared. So because my n value is 2, I'm going to put an n value of 2 down there. Then I'm going to plus, I've got a -1 over 4 factorial, x minus pi to the 4th, plus 1 over 6 factorial, x minus pi to the 6th. Now, not all cosine is even, so if I had done pi over 2, then it would be odd exponents. So you don't always just go with the fact that it's even. I'm looking at this in terms of cosine actually has a value at pi, so then that works. But if you're looking at pi over 2 or something, you won't have even exponents, all right? Just throwing that out there for you. So if I want to look at this pattern, here's the real kicker. So I'm going to make this a negative, like a minus, so you can see that better. I'm starting with a negative sign. So whenever I'm looking at my series here, this is still over 2k factorial, right? We can see that. And we have x minus pi to the 2k. All right? I have an alternating series, but here's the deal. You're starting with a negative. So if I were to just make this -1 to the k, that wouldn't be correct, because I could plug a 0 in, and that would be a positive 1. And that's the issue. You see that? Then if I plug in a 1 here, that should be a negative for the next term. And it's not happening either. So when you're looking at this series, it's directly with this polynomial. I could put a k plus 1 and look how that affects it. If I plug in a 0, 0 plus 1 makes it negative. 1 plus 1 makes that positive because it's even, and so on and so forth. So watch out for that. That's what I would say, is watch out for that. For whatever it is that you have, make sure if it's an alternating series, if it starts with a negative number, then you have to put that plus 1 up there in that exponent. All right. Okay, go try some out now.